Welcome to The Explainer. So let's just jump right in, shall we? Today, we are going to completely dismantle a fundamental assumption that, well, you probably didn't even realize you had. It's this idea that objects exist totally independently, separated by this vast emptiness we call space. We're digging into one of the most mind-bending, reality-breaking concepts in all of modern science, and that is quantum entanglement. Seriously, buckle up, because the way you look at the universe is about to change. Now let's talk about this quiet assumption. It really sits right beneath pretty much everything we believe about the world. Like, you see a coffee cup on your table, right? And you just naturally assume it's there whether you're looking at it or not. You assume that if one thing is going to affect another, a signal has to physically travel between them through space, and it absolutely cannot go faster than the speed of light. It's a comforting assumption. It forms the whole basis of our everyday reality and makes the world feel incredibly stable and predictable.
And you can see exactly how that translates into physics. On one side, you've got classical physics. Think of Isaac Newton's universe. It's like a vast, precise machine where every single thing has a predetermined state. Reality is local, it's objective, it makes sense. But then, you have quantum physics. When we zoom way in on tiny particles like electrons or photons, they completely refuse to behave like solid objects. Instead, they exist in what's called a state of superposition. Before you measure them, they don't have fixed properties at all. They are literally unresolved potentials, basically existing as a whole range of possibilities all at once. So the stakes here are massive. It means reality at its core isn't made of solid things. It's made of shifting potentials.
Which naturally leads us to the big question. What exactly is quantum entanglement?
Well, when these weird unresolved particles actually meet up under the right conditions, they don't just bump into each other and bounce off like billiard balls. They do something that is honestly terrifying to classical physics. Quantum entanglement is an emergent property. The particles literally merge into a single shared system. Scientists at Caltech have this beautiful way of describing it. They compare it to a ballet or a tango that arises from individual dancers. The particles aren't independent entities anymore. They become completely different expressions of one underlying joint wave function. Meaning, even if you separate them by thousands of miles, they are still part of that single system. They are, for all intents and purposes, dancing to the exact same invisible tune.
Okay, I want to pause and break down a super common misconception here. People love to use the glove analogy to explain entanglement. You put a left glove and a right glove in separate boxes. If you open one and find the right glove, boom, you instantly know the other one is a left glove. But listen, quantum entanglement does not behave like gloves. With the gloves, the states were already decided, right? The right glove was always a right glove from the very start. But with entangled particles, neither particle has a predetermined state while it's traveling. They are genuinely unresolved, they're in that superposition right up until the exact microsecond you measure one.
Let's walk through a brilliant little thought experiment to really lock this in. Imagine Alice and Bob have these special quantum coins. First, they take these entangled coins and rocket off in totally opposite directions. Step 2, they travel for, let's say, 10 years, and they never flip them. So these coins are in a superposition. They are both heads and tails simultaneously. Step 3, Alice finally flips her coin, and she gets heads. In that exact instant, the superposition collapses. Step 4, no matter how far away Bob is, his coin instantly becomes tails. Alice doesn't have to wait for a radio signal to reach him. The sheer act of measuring her particle instantly dictates the state of Bob's.
Now, if you're sitting there feeling a little uncomfortable with this, you are in incredibly good company. Albert Einstein found this deeply troubling. Honestly, he kinda hated it. He famously called it spooky action at a distance. And that wasn't just some catchy soundbite. It was a really frank criticism. Because for Einstein, if this instant correlation was true, it meant information was somehow traveling faster than light, which completely violates his theory of relativity. It threatened the very fabric of reality as he understood it.
So, Einstein came up with a fix to save classical physics, and he called it hidden variables. This is the theory that particles carry unseen, predetermined instructions. Basically, Einstein was saying, look, the universe isn't actually playing dice. The particles already know what they're going to be, they just have a hidden label that we just can't read yet. And if that were true, it would beautifully restore local realism, that comforting idea that the universe behaves locally and logically.
And that sparked an epic scientific showdown. In 1935, Einstein and his colleagues published the famous EPR paper, defending this hidden variable idea. For decades, it was just a philosophical debate, people arguing at chalkboards. But then, in 1964, an Irish physicist named John Bell did something unbelievable. He created an actual mathematical test for these hidden variables, now known as Bell's inequality.
Fast forward to the 1970s, and scientists finally had the tech to run the experiments. The results? They consistently violated Bell's inequality. Einstein's hidden variables? They did not exist. Which brings us to the absolute climax of this showdown. Those results forced us to accept a staggering truth. The universe is non-local. This means that down at the quantum level, the whole concept of independent localized objects completely breaks down. Space and distance, they aren't fundamental separators anymore. Two objects can behave as one unified system regardless of how much physical space sits between them. Reality isn't fundamentally made up of isolated things, it is fundamentally made up of interconnected relationships.
But hey, before we start dreaming of faster-than-light sci-fi communicators, we have to look at this crucial point from Caltech's Thomas Vitek. He says there can be correlation without communication. Since the outcome of measuring a quantum particle is entirely random, like you can't force Alice's coin to land on heads, you can't actually use this connection to send a controlled message. The universe absolutely allows this instantaneous connection, but it strictly denies our ability to use it to text our friends faster than the speed of light.
Okay, so if the fundamental fabric of the universe is this strange, non-local, interconnected web of probabilities, why does our everyday reality feel so perfectly normal? Why isn't my coffee cup suddenly popping into a superposition? Why do things seem so incredibly solid and separate to us?
The answer to that very valid question is a process called decoherence. Think of it as the dilution of quantum entanglement. When a superdelicate quantum system interacts with its messy, chaotic environment, the entanglement doesn't just vanish into thin air, it just gets wildly diluted. It's the exact mechanism that hides all this quantum weirdness from our everyday view.
Let's break down exactly how this happens. Step 1. You start with an isolated particle in superposition. Step 2. It interacts with its environment. Just everyday stuff. Air molecules, a photon of light, a bit of heat. Step 3. That entanglement spreads outward, rapidly entangling with all those countless surrounding particles. Step 4. Those sharp, pristine quantum correlations wash out into what we observe as stable, classical behavior. Think of it like trying to hear a single, quiet whisper in a massive, roaring stadium. The whisper is technically still there, but it's completely overwhelmed by the background noise. Our classical, solid world is literally just a byproduct of entanglement spreading way beyond our ability to track it.
Now, let's pivot from the philosophical stuff to something highly practical, the practical quantum future.
Because you see, entanglement isn't just some abstract theory locked away in a textbook, it is a very active tool. Scientists at places like NASA and Caltech are currently working to harness this mind-bending physics to completely change our world. We're talking about quantum cryptography, creating virtually unbreakable security systems, quantum computing, which uses these entangled particles to solve complex problems that would take a classical computer millions of years. We're researching many-body entangled systems to understand completely new materials, and we're developing advanced quantum sensors that can operate in space with just unprecedented precision. We are quite literally betting on entanglement to drive the major technological advancements of the 21st century.
So I want to leave you with this final, truly provocative thought. If quantum entanglement proves that our universe is fundamentally built on interconnected relationships rather than separate independent objects, is the reality we see and touch every single day just a convenient illusion? It really seems like the deeper we look into the structure of reality, the less it resembles the version we actually experience. The surface looks stable, sure, but underneath, everything is dancing together. Thank you so much for joining me on this explainer, and I really hope this leaves you wanting to explore a whole lot more about the weird, wonderful quantum world.